Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is NDS 2024 Mass Timber Design in RFEM 6. My name is Amy Hylake. I'll be your presenter. I'm the CEO of the US office and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Baca and Siska Chora will be your moderators today, answering any questions you may have. They are both technical support engineers, also located in our Philadelphia office. We always want to encourage everyone to ask questions throughout this presentation. You can do so directly in the GoToWebinar dialog box as shown here. If by chance we don't get to all your questions, we will certainly send you a follow-up email afterwards. So regarding the content over the next hour today, we will begin with modeling the structure that you see here. But I'm going to utilize our building model add-on to activate some additional modeling tools that will be helpful for multi-story level structures. We'll talk about the CLT panel layup input, utilizing the multi-layer surfaces add-on. And then with mass timber, a very important topic is how all of these elements are connected together. So we'll talk about some of these special object input like line hinges, line releases, and member end releases. Now, we also have introduced some additional serviceability configurations more catered to the IBC. So we'll go over these improvements with our example today. We also have recently added fire design for both the CLT panels and the timber members according to the NDS. And finally, in addition to running the full analysis of this structure, of course, we're going to carry out the design according to the NDS 2024 for both the CLT panels and the timber members. So for those of you joining us today who are not familiar with our program setup, we do operate with this add-on concept. So RFEM 6 is the base program. This allows us to fully model the structure. We have access to all of the cross-sections and the materials from the various standards. We can apply loads. We can also integrate with BIM software, and we can get a full static analysis. So deformations, internal forces, support reactions are all provided by the base program. Now, specific to mass timber, we would also need the multi-layer surfaces add-on. So this allows us to build up these CLT panels to specify these specific layers. And we can either do this manually or by accessing our manufacturer database. The timber design add-on is also needed. So again, RFEM is providing the full analysis, but we want to take these internal forces and stresses and apply the NDS code equations for both the panels and the members to get those design ratios. Now, there are many other optional add-ons. Today, we'll talk a little bit about the building model add-on for multi-level story structures. We have the modal analysis add-on that might be used for the natural vibrations, the periods accelerations of our structure. But also, I want to emphasize that RFEM is not only used for mass timber, but also hybrid structures. So we have all the US and Canadian codes for concrete, steel design, aluminum, and so on. So with that said, we will begin today in our program RFEM. So when you create a new model, you're presented with the dialog box here, where you'll notice under the second tab are all of the available add-ons. You more or less create a software package that's specific for your project design. Now, for our example today, as mentioned, we do have the timber design activated. We also have the multi-layer surfaces add-on as well as the building model. Now, under the third tab here is where we will set the standards for, first of all, you'll notice the timber design, the NDS 2024, but it should be known that the minute that we activate this timber design add-on, for our load combinations that will be automatically generated, the program does require us to select here the ASCE7 wood. Now, this is really identical to the load combinations of the ASCE7 above it, but the wood allows us to take into consideration the creep factor, for example, and some additional load combinations from the IBC that involve this creep factor as well. Same concept here within this dropdown for NBC and NBC wood. Now, once we have set all of the relevant standards, we are brought here into the main program where we will begin modeling. So the first thing that I want to do is, I mentioned I had activated the building model add-on. Within the building model folder over here on the left, I can immediately begin by defining my building stories. So we right click here to create a new story definition, and the height of the first story will be 10 feet. And we can make a couple additional copies of this for a total of 3 stories with a 30-foot height. Now, within this drop-down box here in the building model add-on, this also gives us the ability to define here diaphragms. So we have rigid, semi-rigid, and what we call load transfer or flexible diaphragms. Now, I did cover the diaphragms in a previous webinar, the CSA 086 Building Design in RFEM 6, so you can refer to that recorded webinar if you're more interested in seeing these diaphragm options for mass timber. For today, I'm not going to apply any diaphragm. So for this, we'll just use the true stiffness properties of the floor, the panel elements, both in plane, out of plane, and for gravity and lateral loading. So once we have defined the stories here, we see back in RFEM just a graphical display where those stories will occur. Now I'm going to right click down here in my drawing grid to edit it, and I'm going to make some modifications to the points. I'm going to set this as 25 points on either side of the origin. I also want to set the drawing grid 30 feet in the Z direction, the vertical direction. So now we see that drawing grid placed up here at the top. So we could move forward then with our CLT surface modeling with an individual surface element or member modeling. But because we have activated the building model add-on, we now have released into the base program here some useful tools for modeling for repetitive multi-level story structures. So what we want to begin with is a new rectangular floor to define here our first CLT panel. So we're presented with the dialog box where we need to immediately define a new thickness. So we create a new thickness definition, and within this additional dialog box, we want to set the thickness type here to layers. Now, layers is only available because we have activated that multi-layer surfaces add-on. Without that add-on, we would not have access to this. So under the second tab, this is where we can begin to define our CLT layup. And there's one of two options here. We'll begin with the first where we can manually create this layup. So within the dropdown, we can create here a new material. And within this additional material dialog box, we can access the material library, where over on the left, we can filter to the United States, to timber, and also to the new 2024 NDS. And then here we have all of the materials as well as the submaterials directly from the code. So if we just pick one arbitrary material here for our example, we click OK. But before we move forward, there's a couple additional modifications that we need to make here specific for CLT. The first is to modify the material model here to linear elastic for surfaces. So we want to be able to define here that this has 2 strengths and 2 different directions for this 2D surface. Now, additionally, we would activate here the user-defined material, and under this second tab, although all the material properties were brought in, I can now set the modulus of elasticity in the weak axis direction equal to 0. Again, quite common for CLT. So once we have made these modifications here, we see the material populate, and I can go ahead and give the layer a thickness of 1.5 inches. My second layer will be the same material, also 1.5 inches, but I'm going to set the orientation 90 degrees here. And this is all based on the surface's local x-axis. So this is the entire intent of CLT, is that we create these layers that are oriented 90 degrees from one another. And for my final layer here, and thickness. Now, once we have created this layup, we can use it to save directly to our library and to pull open in any other RFEM models in the future. Now, the second option here is to go ahead and delete this user-defined option and to access directly our manufacturer library. So within this, you'll notice in the dropdown, we have access to Canada, to Europe, as well as the United States. And here we have all of the manufacturers listed. So these manufacturers have directly given us their CLT products that you as the user can select here. So for example, we will select Mercer Mass Timber for today. We'll filter to the 7-ply layup, and then we can select our relevant product. So when we click OK, you'll notice that all of the materials that were provided from the manufacturer are automatically populated here, as well as the thicknesses. Now, under this third tab, the stiffness reduction, this is a really important topic to understand for CLT. And we'll begin here with the stiffness modification factors. Now, K33 is going to be the torsional stiffness reduction factor, while K8A is going to be the in-plane stiffness reduction factor. And it's quite common for these manufacturers to not place glue at the narrow edges of these boards for each of these layers. So inevitably, we will not have force transfer in those directions. So we want to apply these additional modification factors here to the panel. Now, when we refer to all of the standards and references here in North America, none of them really touch on this topic here. You will notice that they are automatically set when we use the manufacturer library because the manufacturer has given these to us. But if you have manually created your CLT layup, you would want to go in and modify these. And because we have no reference here in North America, we may refer here to the EC5 and in particular the Austrian Annex. And within our website, we have a helpful FAQ here. It's FAQ 4119 that talks a little bit more about these reduction factors, K33, K88, referring directly to the Eurocode 5. It really is just a couple simple equations here. You can even download the Excel file to input in your own properties, and ultimately we'll get the value for these reduction factors to go back into RFEM and input in directly. Now, moving on to K44 and K55. These are the shear stiffness adjustment factors shown here. And you'll notice these are set to 1.0. When we refer to the CLT handbook, the PRG 320, the NDS section 1041, all for deflection calculations, these all reference what we call the shear analogy method. So for those of you that have been doing mass timber for a while, this is probably nothing new. Well, the shear analogy method says, okay, we know that there's a material bending stiffness EI. Well, we must reduce this material bending stiffness to account for the shear deformation. So the shear analogy method further just says, let's take this simplified approach where we simply apply a shear deformation adjustment factor. Well, it should be known that in RFEM, we're actually not taking the shear analogy method. We're going to apply what we call the laminate theory. And we have plenty of resources online about this theory as well as the equations that are used, but the results ultimately match up quite well to the shear analogy method. Again, it's just a different approach, and I would say it's maybe a little bit more exact. But ultimately, the effective shear stiffness of the stiffness matrix entries D44 and D55 are calculated internally, considering both the shear and bending deformation directly. So we could use these equations to back calculate to determine what these reduction factors are, but a new feature that we recently added within this multi-layer surfaces, if we jump to this fourth tab here, is those shear correction factors are now listed. So this will be helpful in just understanding internally what's being used. So therefore, under this third tab here, you probably will not apply additional stiffness reduction factors. Okay, so moving on to our bottom options here for the various shear failure modes. I'm going to jump to the PowerPoint to explain this in more detail. When this option is unchecked, this all just relates to the shear failure modes that we will see once we run the panel design in the timber design add-on. Well, we'll only carry out failure mechanism 1, and this is failure parallel to the grain of the gross cross section. Now, alternatively, if we go ahead and check on this option within that dialog box, we would need to input in the plank width and the plank width including any gaps if that was applicable. But we'll carry out 2 additional checks, including failure mechanism 2 here, which is failure perpendicular to the grain of the net cross section. And we see a nice cross section view here of how that failure mode will occur, as well as failure mechanism 3, which is failure of the orthogonally crossing boards, otherwise known as torsion. So this concept might be a little bit more important for something like a CLT wall element, which is entirely possible to model in RFEM and to design. We don't have any wall elements for our example today. Therefore, we're going to go ahead and leave these additional checks off. Also, most of the standards and resources that we have in North America, once again, don't really discuss this topic, with the exception of the Canadian CLT handbook that does go into a little bit of detail. So you can refer to that for these additional shear checks. Okay, so going back to RFEM here, we'll go ahead and leave this option unchecked. And then I just wanted to point out once again here, we can see the full stiffness matrix calculated for this panel based on the laminate theory. So I'm going to quickly go back to the PowerPoint once again, because I think it's important to understand the huge benefit that we have with RFEM, with this multi-layer surfaces add-on, over software that really isn't meant for CLT analysis and design. So as we just saw, we define each individual layer of this CLT panel, and each layer inevitably has its own stiffness properties. So therefore, each layer has its own stiffness matrix. Well, as mentioned, we're going to take the laminate theory to calculate automatically the overall stiffness matrix of the entire panel, considering all layers. So something like the D11 equation for that stiffness matrix might look something similar to this. So once we have that stiffness, as shown in the dialog box I just showed you, we're going to export this back out to RFEM and to use it in the analysis of the model. We apply the loads, and ultimately we're going to get internal forces on each one of these panels. We take these internal forces and we're further going to determine the stresses and distribute them to each layer of the CLT. So when we're looking at something like a 5-ply layup, the normal stress might look something similar to this. So again, the big advantage here is that RFEM is calculating these stiffnesses automatically. So once we are done defining our thickness here, we're finally back in this dialog box where we can begin by modeling our first panel. So because we're utilizing the building model add-on tools, you'll notice here in the dropdown that I can apply this CLT panel to all stories simultaneously. Again, much more user-friendly for repetitive multi-level story structures. And now I can snap to this grid point, and then my second point here is going to be a 10-foot width. So 50-foot length by 10-foot width. I'm going to do the exact same thing again here, and I'm just going to snap to an additional point, and we could continue to do so, but notice that this is applied to all levels. Now, many different ways to work in the program that we could also select all of these panels here, hold down our control key, and to utilize the drag and drop feature. And maybe we need one more panel at the edge here, so we select the 3 panels at the end, we hold down our control key, and then once again, we can drag and drop. So all of these panels are now automatically generated here. Now this display here is just related to the building model, telling us our mass at each level. We can go ahead and deactivate that under that second tab here if we'd like. Okay, so it is important to know that with CLT, we also have a strong and a weak axis, just like we would have with a beam member. And when we right click here to turn on the local axis system of the surfaces, the strong axis is represented here by the local x-axis, and it's spanning in the long direction, so everything is fine there. Otherwise, we would need to make modifications to ensure that the local and weak axes, or the local x and y axes, are oriented in the strong and weak axis directions. The next thing to do is to draw in our columns. And for this, I went ahead in Excel, populated here the X, Y, and Z coordinates of where all my columns will be located for each floor. I'll go ahead and hit Control C here just to copy it. We'll go back to the RFEM model, and we can work with the table input here. So under structure and under nodes, what you'll notice is that if I scroll down to just a white space here, I can go ahead and click in this cell and hit Control V, and we'll see all of these nodes populate at that top floor. If I turn this into wireframe view, it will be a little bit easier to see. So now that we have those node locations, I will use the building model tools here to draw a new column element. Now, the member type is set to beam. Beam in RFEM is just anything that's a standard beam, a standard column, as opposed to some of the other special member types that we have here in the dropdown. But I'm also going to activate here the hinges. So by default, everything is considered fully fixed. And we know with timber that typically it's going to be a moment release at the member end. So under the second tab is where we would create our first cross-section, and we would access the cross-section library here. So for something like timber, we would probably be utilizing these massive sections, and we would assign a material from the library, but you'll notice here that I went ahead and have already done so. So we'll use this 12 by 12 XLAM column for our first section. And again, we need to define the moment release under the hinges tab. So what we want to do here is to create a new definition type. And the concept of RFEM is to define something once and then to assign it to multiple objects within the model. We don't need to keep redefining each time. So we define here the moment release, we click OK, and then under the drop down box here, we can then select it for the member start and the member end. Now I click OK, and you'll notice that I have the ability here just to snap to these different node points in order to generate the columns at every level. Additionally, I can turn this into wireframe view and go into plan view where I think it might be a little bit easier to see, where again, I'm just snapping to these different nodal points here. And my final couple clicks will be up here at the top, the left, and the right-hand side. So we'll right click to exit out of this, and looking at the render view, we have this bright green color here. This is just grouping together these objects with what we call member representatives. Very user-friendly feature, we're just not utilizing it in today's example, so I'll go ahead and turn it off graphically. Now, I want to emphasize here that, again, hybrid structures are entirely possible. We're not limited to just mass timber. So, for example, if I want to make changes here to my lower level columns, I just highlight them all, I double click, and I'm going to turn off the hinges so I have a fully fixed connection. And under this section, I'm going to toggle these to an already existing concrete section I've defined with 4,000 PSI concrete. I click OK, and now we see those concrete columns generated at the base here, connecting directly to the CLT panel above it. The next thing to do is to draw in our shear walls. And again, emphasizing here hybrid structures, we will draw in some concrete shear walls, but CLT shear walls are entirely possible as well. So we'll utilize the building model wall here. So this brings up the new dialog box where we would, similar to our CLT panels, define the thickness. I've already specified here 4,000 PSI concrete, 8 inches thick, so nothing further to do, but just to simply select it in our dropdown. And then I'm just clicking on these different nodes here to generate the wall elements automatically at each level. So we right click here, and then we have that concrete core. Now, we do need to specify the openings though at the first and second level, because currently we have the CLT panels intersecting with these concrete walls without any opening drawn. So I'll begin by going into a plan view for this, and I'll turn this into wireframe view. What I want to do is in the white space, if you right click, you'll notice the auto connect lines and members is turned off. This just means that things won't automatically create a node where we have an intersection. Rather, I'm going to use this tool up here so that I can manually create those nodes at intersecting lines, which I'll do so within the wall and the CLT elements. Now we have a little bit of a strange symbol shown here graphically. This just has to do with the building model add-on called surface cells that we can go ahead and deactivate as we won't be using them today. But now we need to draw in a new opening. So utilizing the building model tools, we have here a rectangular floor opening, but I don't want to apply this to all stories. Rather, we're only applying this to the bottom 2 stories. So many different ways to work here, but for me, I'm just going to specify here 2 openings, one for the panel on top and one for the panel on the bottom. I right click, and then we can see here in a rendered view how the opening was not applied to this top level, but the openings were applied to these lower 2. Now, the final thing to draw with our elements is our beams. So in a similar fashion, I will go here to draw a new beam element. The dialog box here looks similar to the columns. We want to apply hinges and eccentricities. I've already defined here a glulam section. It's going to be 10 inches by 18 inches with the glulam material. Remember, I've already defined here the member end release, so we can simply select it from our dropdown. But the eccentricities, so assuming that we want to draw these beams that will be supporting the underside of these CLT panels, we maybe want to apply an eccentricity in the model. So we need to create a new eccentricity definition where I can tell the program to take this top point of my beam, and I can offset it from an existing object within the model. So I can select here, for example, one of my surfaces, and we'll select surface number 1 up here at the roof. And I'm going to offset this eccentricity based on the bottom point of the surface. So why would we want to use these offset options, transverse from another object? Well, if we go back in and change this panel to the CLT panels to a 5-ply, or we go in and decide we need to make section changes to our beam, these eccentricities automatically update rather than manual eccentricities that we have to go in and adjust each time. So now that this definition was defined, I can apply it at both the member start and the member end. I click OK. I do want to apply this to all stories. Then I can zoom in here and I can just snap to the top corner points here of my column. And you'll notice that these beams are automatically generated at all levels. Now, again, I'm going to go into a plan view here, and I'll turn this into wireframe to continue drawing these beams. You'll also notice that it's not a problem that we're spanning these beams over multiple panels. And once we're done in the global Y direction, we want to go ahead and create some transverse beams in the global X direction. And then we have one more click down here at the bottom. So once we're done modeling here, I'll go ahead and exit out of this tool. We can turn this back to a rendered view, and now you can zoom in here and see this eccentricity defined, taking into consideration the thickness of the panel as well as the depth of the beam. All right, so finally we want to support this structure. We'll just apply a new nodal support. We're going to take advantage of the already defined fully fixed nodal support. I click OK, and then I'm going to highlight over the base of my columns. I'm going to zoom in here and apply it to these additional 2 columns. It's a little bit difficult to see, so you can always right click here and use our slider tool to increase or decrease the size, and this is available for a lot of the graphical objects in the model. Same concept here for the base of the walls. We apply a new line support. This is going to be fully rigid. We click OK, and then we can highlight over the base of these lines. All right, so now that we have completed the modeling process, let us talk about the fixity of all of these objects together. Now, looking at our top floor here, and we'll start with the CLT panels. So these panels adjacent to one another are considered fully rigid. And of course, we know with CLT, this is not the scenario that typically we want to release the moment and to account for the slip of the connection along this joint. Now, I've seen other resources out there that recommend for FEA modeling, we would need to model in a gap here and possibly fill it in with a dummy surface with reduced stiffness properties. But in RFEM, we have a far more user-friendly option. And what we're going to apply here is what we call line hinges. So over in our navigator, under types for line, you'll see the option to create a new line hinge definition. We just simply double click on it. And we see here 4 degrees of freedom where we can fully release the moment between these 2 adjacent panels. And these axes are all based on the line element itself, not the local axes of the surface element, but again, the line. Now, in addition, we can account for the slip of this connection. So in the direction along the length of this joint, we maybe want to account for the slip. We would input in here a spring constant that we've calculated outside of the program, taken into consideration maybe the spacing of the screws, the diameter of the screws, whatever it may be. So for our example today, we'll just use an arbitrary value of 150 kips per square foot, but you can also add this translation fixity here to account for the slip in the local Y direction of the axes. But for my panel to panel connection, let's just say we want to consider it along the length of the joint. So my next click then is up here where I'm going to first select the surface, and then my second click is just to simply apply the line that this line hinge is applied to. My next click is the adjacent surface, and again the line, and I just continue to move down this top story. But remember, this line over here, we broke it apart into 3, so we do need to make 3 clicks here for each one of these lines, and we click OK. So what we would see then in a wireframe view is a nice symbol here showing us this line hinge. Now notice I did not apply the line hinge to both sides of the line. We want to leave at least one panel fully fixed at an intersection. Otherwise we'll get instability issues. And we would continue to apply the line releases to the rest of the structure. Now, the next topic to discuss is the connectivity here of the beams to the panels, because currently, as we have it modeled here, everything is fully fixed. Well, again, we probably want to release that moment so that we don't have high torsion in our beams. We want to account for the slip in the translation directions. So what we can do is to apply what we call a line release. So line hinges can be used for panel to panel connections. A line release here under special objects can be used for beam to panel connections. Before I do this, I'm going to activate here the building model views where I can activate only the top story. I can right click here to hide all the other objects. I'm also going to turn this into a wireframe view. We just get a little bit better behavior when I break apart these intersection lines of these members. So I'll go ahead and do that similar to what we did for our wall elements. So you can see here, I'm just breaking apart these members at the panel intersection here. And we might be wondering, well, we've now broken apart these members into separate segments, but we can still design them as one continuous member. That's not a problem. So what I can do here is to select all of these continuous members. I can right click and I can create what we call a member set. And this member set will just simply, as you can see here graphically, group together these individual member segments. So again, we can design it as one continuous member. So not a problem there. But again, a little bit better behavior when we apply the line release. So we go back here to the new line release definition type by double clicking it. We create a new line release type here, and this should look very familiar. It should look almost identical to the line hinge where we can release the moment. Now I'm going to set this to a very small value like 0.001, just a little bit better stability when running the analysis. We can also, again, specify here the slip. So this might be different than what we saw with our CLT panel. For example, today we'll just use 50 kips per square foot. We can also account for a slip in the local Y direction, that transverse direction, if we wanted to. So we can go ahead and activate all 3 of these degrees of freedom. We click OK. Now, the next thing to define here is which objects are released. So I'm going to graphically select here all of my beam elements. And we can go ahead and use our selection tool here to highlight all of those beams, and you'll see them highlighted, the relevant numbers, and brought into this dialog box. But the next click should be to the lines that we want to apply this line release. So remember, these lines are being shared between both the panel and the member. So I think the best way to do this is to go into the plan view, and then I can graphically select only the lines here that, again, the beam shares with the panels. I'm not selecting any other lines in the model. But you'll notice that when I turn this around to an isometric view that we have also selected our columns, no problem, just hold down your shift key, highlight these again, and they will be deselected. So again, all of the line elements are automatically selected and shown here and brought directly into this dialog box. So once we click OK, we get the graphical symbol of these line releases. So we would continue to apply the line releases and the line hinges and create those member sets for the rest of the model. But I'm going to open up an already saved model here where that was already done just for the sake of time. We'll now move on to the loading. So within the saved model, I have created a few load cases. Now, remember back when we first created this model that we had set the load combinations to be generated automatically according to the ASCE 7, the 2022 standard. And we can additionally access here that creep factor. So we can set this to something other than 1.5, which is the default. Now, I've already created the load cases by creating the individual load case with this option down here in the lower left corner, assigning the relevant action category. Very simple for today, just a dead, live, win one, win two. So once we've created these load cases, we need to actually apply the loads to the structure. So for dead load, you'll notice here within my dropdown, I can activate the display of the loads, and these are just simple surface loads that have been applied with this tool up here at the top. When we look at the live load, same concept, just with an increased magnitude here. Now we're not restricted to defining loads to the entire surface. We have many different loading options here, including the free loads within this dropdown where we can actually define here areas of these surfaces where the load would be applied and projected down through multiple stories. Now, for the wind loads, I did want to point out here that under the load wizards, we do have the automatic wind and snow load generators according to the ASCE 7 that could have been used on this structure. But again, for just simple purposes today, I went ahead and applied these loads manually. For wind in the global Y direction, you can see this is just a simple line load applied to each of these floors in the lateral direction. Same concept here for wind 2. Again, just a simple line load applied to the floor panels directly. Okay, so now that we have created these load cases, we've applied the loads, we need to combine them together into the load combinations. And because we're automatically doing this according to the ASCE 7, the program will create 3 what we call design situations. And these design situations will be needed later on in the timber design. But for now, you can just think of this as grouping together, let's say, our factored load combinations, our unfactored load combinations. And then we also have serviceability here, which is actually from the IBC. But to begin with these first 2 design situations, for today, I'm going to carry out the strength design according to ASD. So I'm not using LRFD. So what I'm going to do is use this drop down and toggle to ASD instead. And furthermore, I'm going to give this a new name. We'll call this one ASD strength. The second design situation is identical to the one above it. But what we want to use this one for is ASD fire design. And finally, we have this third design situation. And again, this comes from the IBC because the IBC is the only one that really references what to do with this creep factor. Now, we've made some improvements here. So I think our existing users who are joining us today will be quite happy to hear this. But previously, this is pretty much the old way of how we used to create this serviceability design situation that we would group all of these load combinations from the IBC together. Well, this was a little bit limiting in our limiting deflection ratios that we could set. So let me go back to the PowerPoint to explain further. When we refer to the IBC, and we'll go ahead and choose the 2024, the deflection limits are set forth in table 1604.3 that we see here directly in the PowerPoint. And the IBC tells us that we should have different limiting deflection ratios depending on the loading. So we have live or live roof, we have snow or wind, and we also have dead plus live. And furthermore, that the limit set here may depend on the element type. So floor members might have different limiting deflection ratios as opposed to roof members. Well, in RFEM 6, again, we used to just kind of group all of these load combinations together, which limited us to only setting one deflection ratio here. But now we've introduced additional design situations to separate these out that we'll look at in just a minute. Furthermore, once we assign the serviceability configuration to these panels and to these members, we'll see how we can actually input in these values here. And finally, we've always had the ability in RFEM 6 to assign different configurations. Again, something that is a floor element is going to have a different limiting deflection ratio than maybe the roof. So let's go back to the example to see how we can apply that today. Again, we don't want to group all of these together, so I'm going to use my drop down to select here my design situation for live or live roof. Well, I'm going to make a copy of this, and I'm going to modify this to snow or wind for that second design situation for serviceability, and we do it once again a third time with dead plus live taken into consideration that creep factor. So once we go to the load combinations, this will just simply output the individual load combinations belonging to each design situation. So we'll see here the group of the first set of load combinations belonging to ASD strength. The second group here, again, ASD also, but we're going to use these for fire design. And then we have the individual load combinations that will be used for serviceability belonging to those IBC design situations. Okay, so now that we are done setting up the load combinations for the structure, we can apply what we call the configuration settings. So we're technically ready to run the analysis, but the intent today is to also carry out the design according to the NDS. So we've already activated the timber design add-on, and I'll begin here with the surfaces. And I'm going to just highlight all of them, double click to edit. And down at the bottom, you'll notice here that we have this design properties checkbox. So when this option is unchecked, this essentially tells the program I'm not interested in design in the timber design add-on. Rather, I just want to carry out the analysis. But when we check this option, we're going to further have these additional tabs at the top that are specific to the NDS for the actual design process. So we just simply need to move through these tabs one by one, and we'll begin here with the design configurations. So here you'll notice that we have configurations for these panels for strength, for serviceability, and for fire. This is exactly just like how we set up our load combinations. So we'll begin here with the strength. So we go into edit the strength configurations and we jump to the surfaces tab. Now really not much to talk about here. You will notice this conservatism factor for CLT panels for the strength design. This just comes from the PRG 320. This is a 0.85 factor that should be applied to the strong layers only for bending. But also notice that the members are also given here within this same configuration. So again, just some options that we can turn on and off for member strength design. Currently, we're setting this for the surfaces. I just wanted to point out that these configurations are considered together for both the members and the surfaces. So back to the surfaces, we click OK. And now let's take a look at the serviceability, which will be a little bit more interesting. So jumping to the surfaces tab, as I mentioned, what we previously had was this single option up here at the top, where again, we created these load combinations according to the IBC, but you were limited to set one limiting deflection ratio here. Well, we're no longer grouping these together. So we created separate design situations. So I'm going to go ahead and uncheck that. And if we take a look at these additional options here, you'll notice that for live or live roof, we can set our first limiting deflection ratio. But for snow or wind or dead plus live, we have the ability to set different ratios here as well. Now, the same concept also applies to members. We can go ahead and deactivate this first option and notice that we can check deflections for the members in both the strong and the weak axis directions with these limiting deflection ratios set differently depending on the IBC load combinations. We also talked about how we may have different limiting deflection ratios for a roof element versus a floor element. So that's really easy to set in the program here with different configurations. For example, I can type in the name of this first one to roof, and instead of applying it to all objects, what I can do here is just to select the members and surfaces that belong to my roof. I click OK. I can then make a copy of this and I can rename to floor. Now, for my floor, the IBC tells us that we really don't need to check deflections here for snow or wind. So we can go ahead and uncheck it for our surfaces. And if we're already in here, we can also uncheck it for our members as well. And then we would need to graphically assign this configuration to the objects within the model. So all of the objects that are not associated with the roof, we'll go ahead and apply those to. Now notice I also selected the concrete walls. The program's intelligent enough to recognize that this is a timber design add-on. It shouldn't be applied, so we'll go ahead and take those out in the final list here that's populated. But now we have two different configurations assigned to those different objects. Okay, so the final thing here in the configurations is the fire design. And for this, we have a default option here as well, but I'm going to jump to the PowerPoint to talk a little bit more about this feature. So this was recently released that we can carry out the full fire design for both the panels and the members. And when we refer to the NDS, in particular, section 16.2.1, it tells us that we would need to set the nominal char rate here, which is beta sub n, typically to 1.5 inches per hour. Well, then we need to calculate here how these sections are reduced with this char depth, and it should be calculated for each exposed surface. So in RFEM, we would input in, which we'll see in a minute, which element sides are exposed to the fire. We then refer to the equation shown here in chapter 16 for both members and surfaces to calculate what this char depth is to determine the new reduced cross section. And here's the really powerful thing that I highlighted here, that we're going to take these reduced cross sections for both the CLT panels and the timber members. We bring them back into RFEM, and we're going to run through all of those ASD load combinations again. This means that we're going to have new stresses from the analysis. So then we take those new stresses, we bring them back into the timber design add-on, and we're also going to calculate the ASD fire resistance with the adjustment factors given directly in Chapter 16. The resistance or the capacity of these members and CLT panels is different for fire than what it is for strength design. So ultimately, our fire design ratio that will be calculated here, given to us in the program, is the reduced cross-section stresses, again, different from the stresses that we determined from the strength load combinations with the full section, over the fire resistance design strength. So once we get to the design results, we'll take a look at this to see all of this information given to us directly. But back to the configuration settings, remember we're still setting these for the CLT panels. You can see here that you would set the fire exposure time, and then for the CLT panel, which sides are exposed to the fire. Same concept here for members as well, the exposure time, but this time we have 4 different sides to apply the exposure time. And finally, under this third tab, there's that nominal charring rate, that beta sub n. You can see by default that's set to 1.5. So once we have input in all of these configurations, we can move on to the deflection tab. We set all of these limiting deflection ratios. The program just simply needs to know what is L in this scenario. So we can set a different L to use in those ratios differently for each panel. In the dropdown, we can use the maximum boundary line, the minimum boundary line of the two-dimensional surface, or we can manually type this in. So for today's example, let's say we wanted to use the full 50-foot length, for example, we could go ahead and set that here. And finally, under this last tab, the service conditions. This is fairly straightforward. We have a default option. Is the panel dry? Is it wet? What's the temperature? These just all affect the adjustment factors for the capacity. So now that we have assigned the configuration settings to the CLT panels, we would do the exact same thing for the timber members. And we could select a single member, or we could select multiple members here, and we double click. And in an identical workflow, we have the design properties activated, and we would just simply move through these tabs up at the top. One thing that's going to be notably different in CLT panels versus a timber member is we do need to set the effective lengths or unbrace lengths of these timber members. So if we go in here to set a new unbrace length definition, you'll notice here that we can check flexural buckling in the strong and weak axis direction. Maybe I'm not so concerned with lateral torsional buckling because these elements are not so slender, we can completely deactivate it. But under this second tab, the program will default to the full member length here for K times L, or effective length. Now, I've given a previous webinar devoted entirely to member design. This is the NDS Timber Member Design and RFEM 6 webinar, so certainly refer to that if you're wanting a more detailed workflow on the members themselves. But yeah, so we'd go ahead and set the effective lengths in for all of the members. We also have the service conditions here that we've already visited from the panel, same concept. Also the design configurations. Remember I showed you that for strength, serviceability, and fire, that in these definition types, the surfaces and members are included together. But if we wanted to make modifications to that, we could certainly do so. And remember how we created those member sets, even though these are individual segments here, because we broke them apart. Well, for a member set 2, you can also activate the design properties exact same tabs up at the top. So again, you can design this as one continuous member. Okay, so now what we would want to do is to, of course, complete the configuration settings for all of the elements in the model, but I'm going to once again jump to an already saved model here where I have already done so. So you'll notice the results are also run. We'll get to those in just a minute. But once we have completed the configuration input for our members and our surfaces, we would use our drop down here to go to the timber design add-on. So this is just really in table format, and we have the input data and this first tab, design situations. So with the design situations, we've already covered these, that we created the multiple design situations, again, just to group together the load combinations, which they're once again listed here. Well, all that we're doing in the timber design add-on under this second column is just to simply select here the relevant limit state type that should apply to that design situation. So we had here, if we hover over it, our user-defined name of ASD strength. Well, then I'm going to select in this drop-down strength limit design according to ASD. Our second design situation, which was ASD fire, is going to be set to the fire limit state. And then we have the 3 separate serviceability design situations that we simply select the 3 different limit state types here for serviceability depending on live, snow or wind, dead plus live. So pretty straightforward here. Under the second tab, the objects to design. Now, by default, everything is automatically selected here, or we could go in and tell the program, okay, let's go ahead and design all the members I have highlighted here. Remember the member sets as well as the surfaces. So we can individually select objects as well. The other nice feature that, again, our existing users might be happy to hear is that if we go into the timber design global settings here, this is a new checkbox down at the bottom. So previously, if you make any change to the model in terms of the design input, like an effective length, for example, for a single member, this will delete all the timber design results. Well, if we uncheck this box here and we just make a small change to an effective length for one member, that will only delete the results for that one member, not for all of the rest of the elements that are not effective. So this could certainly be a benefit here and a little bit of a time saver to not rerun that calculation. Okay, so now that we have set this information in the timber design, what we would then go to is calculate all, which again, I've already done so within this model. So the results are immediately presented to us within the timber design add-on here in the navigator, this 4th tab. We have the ability to jump to the design ratios on the surfaces. So these are our CLT panels. And furthermore, I could jump to this specific tab here, the design ratios by surface. Now, notice that within the table, I'm currently looking at this surface down here at the bottom. I'll go ahead and turn this to wireframe view. We'll turn off the display of the members. And within the table format for this single CLT panel, we have our group of strength design checks listed first. We have all of our fire design checks listed second, and then we have our serviceability or our deflection checks. Now, every single design ratio is listed here, as well as the layer and the top versus the bottom versus the middle of the layer. Now, if you're not interested in seeing all of this information, you can just simply use this drop down here to filter to the max design ratio for each surface. But focusing in here on the design check details, so we'll go ahead and launch this for shear in the YZ plane. It's a very common question, can we check rolling shear? Yes, we can. So this would be shear in the YZ plane. And you'll notice when I launch these design check details, we can see the demand stresses, the capacity of the CLT panel, and ultimately the design ratio that's given to us here. Some additional options in table format. Now, if we are interested in further seeing how these stresses are distributed to each layer, we can go ahead and activate this button up here at the top. And you'll notice that we can choose within this drop-down the design ratio, or we can activate here the stresses for our 7-ply layup. So we're currently looking at a cross-section view here. Well, within this drop-down, we can view the normal stresses, but we're currently looking at rolling shear, so we can choose tau YZ, in other words, at the shear stress here. And what we would expect to see is the shear stress distribution a little bit higher for these middle layers, and certainly we do. So this is just a little bit more of a benefit here if we want to graphically see how those stresses are distributed throughout our 7-ply layup. But you'll remember here this design check of 0.3. Well, if we jump now to the fire design for that exact same rolling shear check, we can once again launch the design check details. And what we're going to see here is quite a bit different of a design ratio, and it's actually lower, which maybe intuitively doesn't make sense. But remember that, first of all, we're going to reduce this cross section, and we can see this within the table. We can actually see which layers have been fully reduced or partially reduced due to the fire. But the capacity of these CLT panels is also going to be different than the strength design checks because we refer to chapter 16. So all of these numbers are given to us here, and we can see ultimately how this design ratio differs from the strength design check. What's really cool too is that you can activate here the charring depth time diagram that on the x-axis here will show you as a function of time up to 1 hour, because that's what I set for my fire exposure time, how the cross section of this CLT panel is reduced. And ultimately at the end of 1 hour, these are the layers here, whether they're fully or partially reduced, that we export back out to RFEM to rerun the analysis to determine the new stresses for this reduced cross section. Okay, so we can go ahead and exit out of these design check details. Keep in mind too, there's many different display options here. We can view the design ratios by design situation as well. So here's all of our strength checks, fire and serviceability, and then the controlling panel. Now we can toggle here to the design ratios on members. So I'll go ahead and zoom out and I'll deactivate on surfaces and we'll activate on the members. So this is just a graphical view of those design ratios. Now jumping to the design ratios by member set. So remember, we're designing these individual segments as one continuous member. So we're currently looking at the member set down here at the bottom, spanning between the columns. And very similar to the CLT panels, we have our group of strength design checks, fire design checks, and serviceability for the deflection. Now, if we take a look at any one of these design checks, so for example, we'll choose fire resistance for shear in the z-axis, or we could take a look at bending about the y-axis and tension for fire. We launch the design check details. Again, we're going to show you over on the right-hand side here these formulas line by line directly from the NDS with the equation references and ultimately the design ratio that was calculated here. But for this fire design check, similar to the CLT panel, we are going to have a reduced section. So we show all of the section properties of the reduced cross section. We can see a char that we covered in the PowerPoint listed here. And ultimately, the demand, internal forces and stresses, and finally the design ratio. Now for the cross section, we can activate here, let's say the stresses of the reduced section rather than the gross section. So we can view the total normal stresses, or we can view the total shear stresses on this cross section as well. We can activate the dimensions. Now this previously was a 10-inch by 18-inch glulam beam, but because of the fire, it's been reduced here to 6.4 inches by 14.4 inches. Okay, so that should give you an overview of the timber design add-on. I just want to quickly back up in the final minute here just to mention that we also have the static analysis. So remember, this is from the base program itself, and that everything that we looked at was specific to the NDS. But if we back up and jump to the static analysis and maybe one of our load combinations like dead plus live here, we can turn on information like the global deformation. So we can view just a simple deformation of the structure from the static analysis. Furthermore, we can activate here the member internal forces. So we can turn on the axial forces for our columns, or maybe we want to view the bending moments on the beams. And finally, we have here the ability to activate the stresses on the surface for all of these load combinations. So what's really powerful about the CLT panels and utilizing the multi-layer surfaces add-on is that we can view these stresses. But notice when I activate here the layer side, I can turn on the top, bottom, or the middle of any one of these layers, and I can further select the individual layers. So for example, if I'd like to see the normal bending stresses in the X direction of these surfaces, I can activate here layer number 1 and the top. If I'm interested in the negative bending, I would activate here layer number 7, and I would choose the bottom of the surface. And over here in our panel is where we can see how those colors match up to the actual values. And all this information is also given in table format as well. We can view the results by surfaces here, including the basic stresses. We can turn on and off the different options for top versus bottom of these stresses, depending on the layer types. Export them out to Microsoft Excel with the click of a button here to do further sorting. So whether it's the design or just the static analysis itself, pretty complete here with our mass timber structure in the output. Okay, so we will go back to the PowerPoint today to conclude our webinar. If you really liked what you saw today and you'd be interested in discussing RFEM further for your mass timber design structure or any other material, certainly reach out to our team here in Philadelphia. We could set you up with the trial version. We could do even a specific catered online demo to your project types, whatever it may be. You can use this QR code here, which is in the handout in the GoToWebinar, or you can directly contact our Philadelphia office with the information shown at the bottom of the screen with our phone number, and our email is info-us@delubal.com. So we will have many more upcoming webinars. You can register at delubal.com under support and learning webinars. I do tend to send out a reminder email about a week before these take place, and we generally hold about one per month. So at the start of the new year, you can expect to see these start up again. So we would love to have you at the next one. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So this is a requirement of the states that we are pre-approved providers, that in order to receive that PDH, you do need to be here for the full presentation duration of the 60 minutes. Now, if you watched with a colleague or you watched in a conference type setting and you yourself did not register with your own name and your own email, if you could please request the PDH at the email address shown here. Just let us know who you watched it with. Ensure you were here for the full duration, and we would be happy to provide you that PDH. Our email address is info-us@delubal.com. And with that said, I want to thank everyone for attending. And as always, we hope to see you at our next webinar. Thank you.